Hello. The purpose of this video is to derive the Black-Scholes formula. We will be continuing on from where we left off in the previous video, where we arrived at the fact that a call option's price is equal to the risk-neutral expectation of the payoff of that call option in the future, discounted at the risk-free rate. We obtained this through the idea of the replicating portfolio, where we manipulated it until we saw something which is basically was an expectation under some assumptions. We also found out that this interprets as well to the fact that the underlying asset is also equal to the expected risk-neutral expectation of the payoff of the underlying asset. And that was achieved through the concept of no arbitrage. Now, the important thing over here to note is that the risk-neutral measure has a property which states that discounted asset prices have to be martingales. So let me just write this down. So when we say that, what are we actually meaning? Well, if we're dealing under the risk-neutral measure, let's think about it. When we're dealing under the risk-neutral measure, we don't have any risk, and therefore the only expected return that we should receive for our investment or should be simply the risk-free rate. And by saying that discounted asset prices are martingales, we're essentially saying that taking into account that we will obtain the risk-free rate, then we have basically a zero return. So let's just recall what a martingale is. And a martingale is basically a stochastic process which has it such that the expectation of that asset, call it X, at capital T, given all the information up to time little t, is equal to little x, x little t. So in essence, what we're saying is that the expected value of the future of that asset is simply the value of the asset today. So we don't really expect any return. So how can we see that from this formula over here? Well, we can do so by first off just using the notation little t. So now instead of looking at it as if we're starting from the beginning in time, we will generalize the concept by having it start at any point in time before expiry. And we're doing so to show as well that we're dealing with basically martingales. So let me now just continue on from where we left off, where we said that the value of a call option under the risk neutral expectation is equal to the risk neutral expectation of the payoff of that call option. And now we need to discount it back, but we're discounting it not simply all the way from t to 0, but from t to little t. So, and that is the distance over here. And we have a filtration, which basically states that we have all the information up to time little t, because we are at time little t. So next we just need to simply multiply both sides of the equation by e to the power of negative rt, which eventually leads us to this equation over here. And if we call discounted asset prices, or in this case, discounted call option prices, if we call them Y, then this is what we get. And what is this? Well, it's a martingale. And hence, we showed that the property of the risk-neutral measure. Okay, so before we move on to the Black-Scholes model, we need to understand how do stock prices actually move. And the way in which Black and Scholes model stock prices was using something known as the geometric Brownian motion. We'll call it GBM over here. And mathematically, that basically states that the value of the stock is equal to the initial value of the stock multiplied by e to the power of mu t, where mu represents the expected return, plus sigma, which represents volatility, multiplied by a random process over here. And this random process is a Brownian motion. And a Brownian motion is useful for a number of reasons in finance. First off, that the increments of the Brownian motion, which you can think of as returns, are independent of the past. And that ties in nicely with the efficient market hypothesis that we don't really expect for prices to reflect the past. Otherwise, people would make some arbitrage if they can predict something about the future based on the past. And the second thing is that it is normally distributed with a mean of 0 and a variance which is based on the time period. And that normality assumption is a good starting point to assume for stocks. However, it's not always going to be the case that stocks are normally distributed. However, it's a good starting place for a number of reasons. One of which is that we have something called the central limit theorem, which states that things tend to normality when we have enough observations, and if these observations are independent. So finally, one last thing to note is that the increments of the Brownian motion exhibit something called strong stationarity, and that is dependent on the increment time period. So if we have two increments of the Brownian motion and they have the exact same time period, so for example, WT minus WS and W X minus WY, and the difference between T and S and X and Y are exactly the same, then we would realize that they have something called strong stationarity, where they have the same mean and the same variance and the same distribution. So that's Brownian motion in a nutshell, and that's why people tend to use it in finance as the first stepping stone. And note that now we're moving away from discrete discrete time pricing, to continuous time pricing. So we're no longer dealing with binomial trees as we did in the previous video. But now we're dealing with something which is continuous, where prices could change every millisecond or every whatever, and that these prices are all continuous. So having said that, this is how we would model stock prices according to Black and Scholes. And the reason why Black and Scholes don't simply use a Brownian motion is because, first of all, Brownian motion is centered around 0. And the way that a Brownian motion works is that it has a mean of 0, and therefore prices could go up and down below 0. And that's not really how we thought of prices, at least in the past, because now obviously we can see that prices go down, but generally for stocks we expect there to be a lower bound of 0, and that is achieved through the geometric Brownian motion, because the lower bound of e to the power of of anything is 0, and the upper bound is infinity. So what we would have is a bound between 0 and infinity. So now let's move on and look at the actual problem, which we are trying to actually come up with a closed-end formula, which is the call option formula. So again, for the reproducibility of this model for pricing any call option, whether it be at time 0 or time little t, we're going to stick with time little t and basically this equation over here. And we're going to rewrite this formula by expanding the call option into its components, which is simply st minus k, given that st is greater than k. And recall that we also have a discount factor over here. And of course, we add the filtration, which basically just states that we know everything up to time little t. Now we can take a few things out. So first off, we can take the discount factor out because they're all constant. Time is a constant and r is assumed to be a constant. That is one of the assumptions of the Black-Scholes model. And before I move on, I would just like to note that in the previous video, we showed that the risk-neutral expectation formula, i.e. how we got to over here, was basically through manipulation of the replicating portfolio, where we had a few assumptions so that the probability is valid. And one of the assumptions for that was that there would be no arbitrage in the market. And hence, we arrive at our second assumption and are able to understand where these assumptions for the Black-Scholes come from. So moving on, what we're going to do next is we will just simply split this out a bit further by taking e to the power of negative r multiplied t, capital T minus little t, multiplied by the expectation of st, given that st is greater than k, minus the k multiplied by the expectation. We took k outside the expectation because it is a strike price which is constant, and we will simply have that as the indicator function where st is greater than k. Of course, we have to just rewrite that we have filtration over here. Okay. So now what we need to do is solve those two parts of the equation. We'll start with the right-hand side. So what we want to try to solve is the following. Now, what is the for now, I just want you to ignore this notation over here. We'll get to that in a minute, but we're just simply taking the expectation of the indicator function. And what is the expectation of the indicator function? Well, it's equal to the probability of st greater than k. And it's quite easy to figure out why this is the case. Assume basically the very basics of what is expectation. Well, expectation is basically probability multiplied by the possibilities that are out there. And what are the possibilities that are out there for the indicator function? Well, it's simply probability of st greater than k gives us 1, and the probability that st is less than k gives us 0, and anything multiplied by 0 gives us 0, and therefore we're left with probability of st greater than k multiplied by 1, and hence we arrive at this. This is just a quick info in case people are wondering how we got from expectation to probability. And now what we're going to try to do is get the probability, get the stock to be in the geometric Brownian motion model. So we will have the following. And apologies, I think, yeah, that's not little t, that's capital T, because that's where the payoff is at, and we're basically saying it is greater than k. Now, the question is this actually right? And when I'm asking that, am I saying, is this true that we just have this sort of information? Well, the answer to that is no, because we are already at little t. So in essence, we already know what's happened up to time little t. So it wouldn't be right to say what's the probability of st being greater than k without accounting for the fact that we already know where s at little t is. So what we're going to try to do is slightly alter this formula by saying that we want st, which is equal to ut plus sigma wt, little t, and since we added both of those, we need to subtract them, and by subtracting them, we would be left with u and sigma wt minus wt. So in essence, we added ut and sigma wt, and therefore we subtracted the u multiplied by negative t over here and sigma multiplied by negative wt over here. So in essence, we didn't change the formula, we simply expanded it so that we get this to be the form of s of little t. And we're saying that all of this again is greater than k, given the information that we have up until that point in time. So rewriting this, we will just say that we have st multiplied by e to the power of mu t minus little t plus sigma wt minus wt. And we're saying all of this is greater than k, and since we greater than k given all the information up to today. Now, since all the information, we know that s of t is already, we can already read it from the expectation and everything, and these are all constants, or at least things which do not depend on the past. As we said, the increments of the Brownian motion are completely independent of the past. So this is independent of the past, and this is constant, and this is known at time little t, and this is a constant. So therefore, we don't really need the filtration anymore, i.e. we can simply say it's a probability as this. And then what we're going to do right now is we're going to try to manipulate the equation a bit more by taking st to the other side, i.e. dividing both sides by st. And now we're going to take the log of both sides. Now we're going to have everything except the increment be on the other side. And now what we're going to do is we recall that the increments of the Brownian motion are normally distributed with a mean of 0 and a variance which is equal to the time period. So what we want to try to do right now is standardize this and basically divide this normally distributed variable by sigma, which would enable us to have it be a standard normal distribution. So let's do that. So we'll call the new distribution x, for instance, and we're going to say that that's basically because we divided it by the time step, and if we divide on this side, we also have to divide on that side, and therefore what we have is log of k st minus mu t minus little t, all of which is over sigma t minus little t. It's the square root of t minus t because the variance is t minus t, and therefore the standard deviation is the square root of t minus little t. Okay, so we're almost done finishing the first part of the equation. Now, what is next is that we will simply take minus the normal distribution of and all that we're saying over here, imagine this is a normal distribution. Sorry for the lack of asymmetry in this picture. And we're saying basically what is the probability that x is less than this value over here. So we're looking at all of this side. So in essence, what we need to do is figure out. What I did over here is basically this normal distribution shows us all the area which is over here in this side. And what I had done is take 1 minus all this information, all this thing which is less than this value over here. And so if I subtract 1 minus all this information over here, that gives us this value which we are actually trying to find. And this eventually equates to taking 1 minus n. From statistics, you know that this is equal to n with the negative inside the brackets. So negative over here, meaning that we can simply take st over k, log of st over k, plus mu t minus little t, all of which is over to sigma square root of t minus little t. That is the first solution to the first part of the Black-Scholes equation. So we'll continue on the second part and the concluding things in the next video. But I hope you understood a little bit more about the way that Black-Scholes is conceptually derived. And I'll see you in the next video. Thank you very much for listening.